Hello everybody, and welcome to the last round of our Math Counts collaboration for this year. If you were here the last two times, which were yesterday and the day before, we talked about the Math Counts competition sprint round, Math Counts chapter competition sprint round from 2020, which was earlier this year. If you're new to this, Math Counts is it's the biggest math tournament in the United States for middle school students. And it brings people from all of the different schools all across the country to go and try to see what they can do to challenge themselves against hard math problems. The chapter competition happens to be the competition that people take at the city level. So if you happen to be representing your school in some form, you would go to this contest and you'd meet other very interesting people from all around your city. In the chapter competition, there are two main individual rounds. One of the individual rounds is something where you try to do 30 questions in 40 minutes. It's called the sprint round, where you try to sprint as fast as you can. The second part of the competition is called the target round, and that's what we're going to talk about today. The target round has 8 questions, and for each of these questions, they come actually in pairs. They come in 4 pairs of 2, and for each of those pairs of questions, you get 6 minutes to think. That's not what we're going to do here. We're just going to go through these 8 questions on the target round without really paying attention to that time limit. Also in part because the best way to learn from the questions is actually just to do them. Alright? So don't worry too much whether you're fast or whether you're slow. The interesting thing is to look at the problems and see whether you can come up with solutions. If you notice some people in the chat seeming to solve the questions instantly, it might be because we shared all the problems in advance. And so in some sense, this video was ideal for people who have already played with those questions. If you're watching a recorded version of this video, I encourage you to go back and first play with those questions, or press pause every time you get to a new question picture like this. I'm going to tell you, I actually have not done any of these problems yet. So I might get some wrong. We'll see. That's just how the real world is. But I'm doing it for a challenge. So let's see what we can do. I've also learned from experience last time, as we did the sprint round, that the questions get much harder as we get towards the end. So this time, what I'm going to do is if I see a question and we can do it relatively quickly, we will, in the hopes of maybe finishing on time. We'll see. Let's see what happens. Okay, one other thing about the target round. You actually are supposed to be able to use a calculator. So that reminds me, I should bring over my calculator. This is not really the calculator you're allowed to use on the competition, but all I'll do is simple calculations, and I'll tell you whenever I'm doing those, so that you can see, you can keep me honest. Okay, let's get started. Question 1. What's this one about? It's about Natasha. Natasha received 14 candy bars at Halloween, while her younger brother Soren, is that right? Let me go and make this a little bigger, because at this point I'm not only testing my math, I'm also testing my vision. Natasha received 14 candy bars, her younger brother received 8. How many candy bars must Natasha give Soren to ensure that they both have the same number of candy bars? Aha, these kinds of questions. Gee, well, it looks like they're going to go and share candy bars, right? So there are 14 on one side, there are 8 on the other side. 14 minus 8 is 6. Don't fall for that. All these kinds of questions, especially at the beginning, it's like, come on, just 14 minus 8, it's 6. But if Natasha gave 6, Natasha would have 8, and Soren would have 14. So it shouldn't be that. They should meet in the middle. It should be halfway. So the way I often think about this is something like, well, Natasha has 14, Soren has 8. And what they want to do is they want to meet in the middle. If they want to meet in the middle, well, there's 6 to go in between, so each side has to move halfway. So each of them has to move by 3. And so my idea of the answer is, it looks like the answer should be 3. Let me ask my assistant. How are we? We're good! Okay, so we got this one right. Let's keep going on. Next question. And you can see I'm nervous now because I know that these questions might get hard. In the coordinate grid shown, what is the area of the shaded quadrilateral, all of whose vertices are on lattice points of the grid? The word lattice points, if you're unfamiliar with that, that just means that all of the points happen to be like whole number, okay? So let's look at this picture here. Oh, I need to find the area of these things. These are fun. These are always like puzzles where I try to cut apart the picture into some things that are easier to calculate. What a weird picture. But it's 2 triangles. Oh, interesting. Somebody said you can use Pics Theorem. You can also use Pics Theorem. Pics Theorem is a theorem where what you'd say is you'd try to count all of the points inside it, count the points on the boundary, and so on. But actually, that's harder. What I'm going to do instead is I'm going to just cut this. Zoop. Now I've got two triangles. Let's go and find the area of each triangle. Now I have to go and count. Counting is really hard. So I have on the base of the first one, it goes from 1 up until 7. That sounds like 6. Just double checking. Looks right. So it looks like we have 6 units on this part. That looks like it's 6 this way. We're going to do half base times height. How much is the height for that little guy? Well, the little guy looks like it's got 3 up and down. Goes from 1 to 4. Okay. And so I know now my answer is so far going to be 1/2 of base times height. So 1/2 of 6 times 3 plus, what's the other one? So I need to go and find the other piece. The other piece, what's the base? So the base goes from 7 to 12. Notice that I'm doing it where I'm not going to count. Counting is very dangerous. It's easy to count wrong. But it's a lot easier to subtract. 12 minus 7 is 5. So it looks to me like this distance should be 5. 12 minus 7. Here's another thing I'm doing just to double check in my head. Somehow in this picture, it's very convenient that the numbers are 2, 4, 6, 8, 10, 12. They're every other one. So I also do a checking by oddness and evenness. So since I saw that it got to an even number, but it started from an odd number, that helps me to double check that my answer should be an odd number, because even minus odd is odd. Okay, how about the height? Well, the height here, it goes from 1 up until, I've got to look closer, 1 up to 9. So if it goes from 1 to 9, that's a height of 8. So this one is 8 tall. Okay, let's add the other piece. So plus 1/2 times the base times the height. So far, it looks like these will be nice whole numbers. I think we're going to be in good shape, because 1/2 times 6 times 3 is equal to 3 times 3, which is 9. And 1/2 times 5 times 8, the half of the 8 is 4. 4 times 5 is 20. It looks to me like we're about to get an answer. So it looks to me like the answer here is 29. And I'm reading the question again to make sure that's what it was asking for. And it looks like we're good. So it's good. So the answer is 29. And you'll notice the last thing I did was read the question again real quick to make sure that I didn't get the wrong problem. And we're good. Okay, what is a lattice point? Andy Shu asks. A lattice point just means that the intersection happens to be at whole number, comma, whole number. So this intersection happens to be exactly 9 tall, at a y of 9, and at an x of 7. Okay, good. Next question, let's go. Ooh, nice. Next question. This must be question number 3. Polynomial. If the polynomial 5x minus 3 is a factor of the polynomial 5x squared plus 7x plus k, what is the value of the k? Oh, interesting. I see 2 ways to do this already. So, and I'm going to talk about the 2 ways just because I want to teach something here too, okay? So here's one way. One way is to say, if I have 5, let's use green just because that 5, the white looks like the problem statement. 5x squared plus 7x plus k is supposed to be equal to 5x minus 3 times. How can you finish this? Well, if I want to finish this, I would need to multiply 5x by something to go and make the 5x squared. And so that would be the x. If you have experience multiplying these things together, it'll always be something x minus or plus something x minus or plus something. And how you make the x squared term comes from these 2 joining, okay? And then the other piece, I don't know yet. Let's just say plus blank. I don't know what that blank is. We'll find out. But what do I need to know about the blank? That's how I make a 7, right? The way you make the 7 is that it comes from 5x times blank minus 3x is 7x. So let's just make a note of that. So I need to know that, let's do it here. So I need to know that the 5x times the blank, let's write it this way, 5 times the blank times x. Let's write parentheses, meaning we're multiplying. 5 times the blank times x minus 3x is supposed to be equal to 7x. So that tells me that 5 times the blank is equal to 10. Okay, and I just said, like, you know, I'm comparing coefficients. I'm saying that's how many x's I have. So now I know blank is 2. So if blank is 2, I'm going to quick do a double check. 5 times 2 is 10x, minus 3x is 7x. It's good, and I get minus 3 times 2. Oh, that's minus 6. So let's see. So if I actually expanded this thing out, I would get 5x squared plus 7x minus 6. And so I'd get an answer of minus 6. That's the check, and we're good. But let me tell you another way to do this problem. There's another way to do this problem where you don't even need to do all this multiplication. Okay? So look at this. If I look at this thing here, pretend I didn't know what was the blank. Okay? I'm going to write down that I say 5x squared plus 7x plus k is equal to 5x minus 3 times something. All I'm going to tell you is something. The something even has x's in it. What happens if I substitute x equals to 3/5 on both sides of this equation? If you substitute x equals to 3/5, does anyone see why I chose 3/5? If I substitute 3/5 into the right side, what happens? This is an interactive live stream. You can answer if you wish. Aha! There is something interesting that happens here. When you put x equals 3/5, 5 times 3/5 is 3. Minus 3 is 0. So you get 0 times, I don't care, 0. The right side is going to be 0. You see, the right side would just be 0 times who cares? I guess that's not what you're really supposed to write in algebra class, but that's what I'm feeling like right now. It's who cares? It doesn't matter. It equals 0. And over on the left side, what do you get? You get 5 times 3/5 squared, whatever that is. I know what that is. 3/5 squared. Oh, that looks like an x. So 5 times 3/5 squared is 3/5 plus 7 times 3/5 plus k. Just enough space for my k. Equals 0. So in that case, I could figure out what k is. Boom! So let's just figure this part out. What happens here? Let's do some canceling. 5 cancels the 5. So I get 9/5 plus 21/5. That's 30/5. 30/5 plus k is equal to 0. So that's 6. 6 plus k equals 0. K equals -6. Both of these work. I personally prefer the second method because the second method is actually safer. If you just look at this, you're like, I want to use 3/5 as what I plug in for x, and the whole thing needs to zero out. Okay, that was question 3. Let's keep going because we don't know if the questions will get insanely hard as we get towards the end. Okay, question 4. The movie sequel, Cat Lawyer 2, The Perfect Crime. Oh, you guys are so funny. Okay, grossed $35.3 million during its opening weekend by selling 4.29 million tickets. Based on this, what was the average price per ticket during opening weekend for the movie? Huh. It looks to me like this is a division problem. Okay. Why is it question number 4? Now I'm actually getting kind of scared. Usually the way the chapter round works is that the first question in every pair is easy, and the second question in every pair is hard. And question number 4 is the second question in a pair. But it looks to me like all I need to do is just divide. How could that be? I have to just divide 35.3 million by 4.29 million? I guess. Okay, so that seems a little bit odd. Now I'm reading the question again. This is actually exactly what I would do during a competition. It's like, why is this so easy? Because I even get to use a calculator. Well, let's first see if it works. So I do get to use a calculator. Here comes my trusty calculator. I want to divide 35.3 million by 4.29 million. Forget about the millions. I'm just going to divide 35.3 divided by 4.29. Okay, 35.3 divided by 4.29. The reason I'm doing this is I'm curious what the answer is. Huh. So now, that's a little funny. So when I do that, then I get a number which is not a whole number. So at this point, I'm going to say, let me read the question on the actual paper. I have a version of the problem that's transcribed onto a slide. What do we have here? 35.3. Oh. Okay. gross this much by selling this many tickets. Okay. Oh, wait a second. No, that's fine. So if I have 35.3 million divided by this, now I'm actually very, very curious because my answer has some rounding inside it. So now I'm actually very curious. Okay. Because usually on math counts, it would tell you to round to the nearest cent. So you can see this is exactly what I would do. I'm like, something's fishy about this problem. Grossed $35.3 million. I'm looking at the thing, selling 4.29 million tickets. Huh. Seems good. Okay. But that's still fishy. The reason I say that's still fishy is because I just divide these numbers. I take the 35.3, don't worry about the million because I'm dividing by millions, divided by 4.29, and what I seem to get is 8.228, and it keeps going. Okay, so I could actually get this wrong. I'm not sure. I think the answer is 8.23. So I'm going to say the answer is 8.23. I'm going to say 8.23 is the average price per ticket, and my assistant says, oh, it's correct. Okay, in that case, we're safe. It's correct? Oh, it's correct. Okay, okay. You can see, by the way, the reason I'm being very careful is because sometimes on math counts problems, you have to be very, they can be tricky in the way it's written. And also, usually you don't have to round unless it says to round. But I guess we're okay. Okay, so then we're fine. Let's keep going. You can see I got more scared on this one than maybe we needed to be. Question 5. What's next? Question number 5. These people's names are so funny. Addy, subby, multi, and divvy are given two distinct non-zero numbers. Addy adds the two numbers. Subby subtracts the lesser number from the greater. Multi multiplies the two numbers. Divvy divides the greater number by the lesser. Okay, here's where I'm reading carefully. I'm like, divvy's doing something backwards. Greater by lesser. And subby subtracts the lesser from the greater. So subby's answer will be positive, and divvy's number will be less than 1. I'm just being careful of reading. If the results obtained by addy, multi, and divvy are the same, what is subby's result? That's cute. Okay, let's find out. Let's give the numbers some names. So I need to know which one is smaller and which one is bigger. So I guess I have two numbers. My numbers, let's call them x and y. Say the numbers are x, and x happens to be less than y. Now let's see. So apparently addy adds x plus y, is the same as what happens when multi happens. Multi is x times y. And also addy gets the same thing as divvy. Oh, this is where I can decide which I want to use for my two equations. You see, I've got two unknowns here. I could say x plus y is also equal to the greater divided by the oh wait, no. Actually, no. What I said earlier is fine. Divides the greater number by the lesser is actually a number bigger than 1. Okay, so I'm reading carefully, and actually it's okay. So the divvy is doing what you'd expect to like have a number bigger than 1. What I said previously was wrong. But so I could say x plus y is equal to y divided by x. But that's not as convenient of an equation as to write x times y is equal to y over x. You see, I could either have written x plus y is y over x, or x times y is y over x. This is nicer because I can do some multiplication and division. So now when I look at this, first I want to double check divvy does divide the greater by the lesser. That's what happened here. So now I've got this. The first thing I want to do is I want to simplify this piece out. Let's divide both sides by y. That only works as long as y is not 0. So then we need to look, is y 0? Oh good, it's not. We're guaranteed that they're non-zero. So I can divide both sides by y. Once I divide both sides by y, I find out something interesting about x. X equals 1 over x. Or in other words, x squared equals 1. That means I've got two choices for x. X is either plus 1 or minus 1. I wonder which. Let's find out. I've got two cases. That's how you usually do these problems. Let's look at the two cases separately. Case 1. X is equal to plus 1. If x is equal to plus 1, actually this thing automatically happens because 1 times y equals y divided by 1. And so I just have this equation left. 1 plus y equals 1 times y, which is y. Is that possible? That seems pretty hard to do because 1 plus y is always going to be farther ahead. It's sort of like if you happen to have a younger sibling or an older sibling, it's like you'll never be the same age as them because the difference will stay the same. So in that case, this case is no, does not happen. How about the other case? x equals -1. Now, when I look at this equation, it's still good. But when I look up here, I get -1 plus y is equal to -y. Now, that is possible. Let's add y to both sides. I get 2y. Add 1 to both sides is 1. Aha, y is equal to half. Let's see, does this work? So what we're finding out here are the two numbers are -1 and a half. Let's check. I want to double check this before I keep going. Is it true that adding them gives you half? Sorry, adding them gives you -half. What happens when you multiply them? -half. What if you divide them? The greater by the lesser is, wait a second, something's fishy. I'm looking at this thing again. Did I do a mistake? So divi is where you divide the greater by the lesser. Ah, the greater is half. Half is greater. Divide by -1, that's equal to -half. They're all -half. What is subby's result? Subby's result is to subtract the lesser from the greater. A half minus -1. The distance between them is 1.5, or 3 halves as a common fraction. So I'd put the distance between them as, if I subtract, I get an answer of 3/2. Common fraction in math counts means you write it as something over something. And we're good. It's good. Okay, this is the answer. Let's keep going. Question number 6. Ooh, what's this funny picture? 3 geometrically similar George Washington profiles. Oh, that's George Washington. Oh, this is hilarious. I know that because I've seen a quarter before, and that's the picture on the quarter. All right. 3 geometrically similar George Washington profiles. A profile is if you look at a face from the side. Are attached to the sides of a right triangle. Who in the world would do that? Oh, well. With leg lengths of 6.2 centimeters and 9.3 centimeters. Does that say 9 point? Yeah, it does. Oh, it looks like your screen might be slightly cut, but that's okay. This is a 9.3. And just so you know, that says 9.3 centimeters. All right. The height of the profile, yeah, is equal to the length of the side. Ah, yes. So it's saying that George Washington's head on top and is the bottom of the neck on the bottom is right there. And I guess everything is proportional. And now, oh, I see. If the largest profile has an area of 25 square centimeters, what is the area of the smallest profile, shaded here in purple? All right. So it looks like what we have to do is we need to look at the ratio of areas. And the ratio of areas of objects is the square of the ratio of their length, of their one-dimensional thing. You can say that, this area is a two-dimensional thing, and if you want to know what happens to two-dimensional things, if you scale them by a factor, the area scales by the square of that factor. And so when I go back over to here, I need to know what is the factor between this hypotenuse and this leg. I wonder if there's a picture that I can use on the next screen. Let's see. Yes, there is. And this one you can also see the 9.3. All right. When I look at this, I don't want to do the Pythagorean theorem with 6.2 and 9.3. Those are really weird numbers. Instead, I'm looking for some kind of a common factor, okay? And so the common factor here, if I look at 6.2 and I look at 9.3, they seem to have I guess when I look at it, it seems like it has a 31 inside it. It has a 3.1 because 3.1 times 2 is 6.2 and 3.1 times 3 is 9.3. So what I'm going to say, I'm going to say that this picture is the times 3.1 of this picture. 2, 3, right triangle. And what goes there, the Pythagorean theorem just tells you, is the square root of 2 squared, which is 4, plus 3 squared, which is 9, which is the square root of 13. That's a strange looking one. Let's draw that a bit better. Square root of 13. And now I'm going to save a lot of time. You see, the ratio of the hypotenuse divided by this one leg is the square root of 13 divided by 2. Or in other words, actually what I'm more interested in is what's the ratio of the leg divided by the hypotenuse. So I'm going to say in this little triangle over there, the vertical leg divided by the hypotenuse, that's equal to 2 divided by square root of 13. Okay? And that's just what's going on this picture. But that will be the same as over here. because these two triangles are just scaled versions of each other. If this one was 2 divided by root 13, over there that's also 2 divided by root 13. But now the question I'm asking is, what's the ratio of the square of that ratio? Sorry, what's the square of that ratio? The square of that ratio will be the ratio of this area divided by that area. This is why I'm not going to even worry about this 3.1. I just want to directly use George Washington's 25 square centimeters. Okay? So that's what's going on here. That means that over here, the ratio of the areas, ratio of yellow to blue, yellow area over the blue area, that's just going to be equal to the square of what I had before. So that's 4 over 13. Now, this will save us a ton of time. 4 over 13 is the ratio of those areas. But I know this area is 25 square centimeters. That means that the yellow area is 4 over 13 times 25, because the blue area is 25. So that means that the yellow area is equal to 4 over 13 times 25. Something like this makes me wonder what format is the answer supposed to come in? Oh, expressed as a common fraction. So that's good. I don't even need my calculator. I actually don't like calculators. Okay, I like multiplying. 4 times 25 is 100. So I'm getting 100 over 13. Don't tell me if it's right or wrong yet. I want to read the problem again. And the reason is because I see that I've got some time. And whenever I have some time, I want to use the time. By the way, you'll notice that I was speeding like crazy through because I was like, I don't know if we'll get through all the problems. Do you know why I actually know we have some time now? It's because it's barely 4:30 yet, and it's not even 4:30 yet. And we only have 2 more questions to do. And the time limit for those 2 questions is 6 minutes on the actual competition. So something's telling me that I actually had enough time, and we are not in a horribly time-constrained situation. And this is also a lesson to you if you're doing a contest. Never be like, I'm done, I'm just going to go kick up my legs and, look at the ceiling. The ceiling's pretty boring anyway. It's usually just white. But anyway, I now want to go and read the question again. Is that what I needed to do? Read question. Okay, so yes, I think, yes, all of this makes sense. My interpretation was right. And the area of the smallest profile. Oh, here's where I'm reading some little cute things about, it's the smallest profile. Yes, it is the smallest profile. That's the side corresponding to the 2. And I need to know what it is in square centimeters. Is that right? Probably, yeah. Okay, in that case, I don't even need to do a unit conversion. And so I'm going to propose the answer 100 over 13. Are we good? Yes, and it's good. Okay, so then here we are. I want to emphasize, especially with the target round, if you are playing the math counts competition, in the target round is when you often do find yourself with like another minute or 2 when you're, I don't know, twiddling your thumbs or something, being like, I don't know what I should do. I think I'm done. But it's actually very often that you do that. And then after 2 minutes, it's like, time's up. And you find out that, oh my gosh, it wanted a mixed number instead. You know what I mean? So if you ever have time left, just go back and read the question again and see what you have. Yes. Okay, let's see what we've gotten here. Next question. Number 7. Can we finish the last 2 in half an hour? I sure hope so. Well, what that means is we'll probably have some fun talking about something else. Famous last words. This is probably going to take me the whole half hour. Let's see. A fancy picture. The polygon shown is a dodecagon. Dodecagon. That means 12 sides. Dodeca is 12. Deca is 10. And there's also something called a dodecahedron. It's a 12-sided polyhedron, 3-dimensional shape. And it says it has 6 diagonals, each with length 10 meters. Dodecahedron, should it have 6 diagonals? I guess so, because you're sort of connecting the things across from like opposite sides. So that would make sense that you would get 6 diagonals. It's almost like if you looked at a clock. A clock is sort of like a dodecagon. Oh, but this is not exactly like a clock. They're not equally spaced. Each of these is 10 meters long, and they all intersect at the center. The polygon has 8 sides of length root 10 meters each, and 4 sides of length root 2 meters each. What is the area of this dodecagon? Okay, if I look at something like this, I say, where's my information? My information comes from side lengths. I've got some. And it also comes from the diagonals. But the diagonals are each of length 10 meters. So let's quickly go and label something. Each of these is 5. At that point, I'm already happy. The reason I'm happy is because I see that this is made of two different kinds of triangles. I care about the area. If all I need to do is find the area, and I've got two kinds of triangles, let's just find the area of each triangle. So I've got two kinds. Let's go ahead and start with one of them. Let's see if there's a new picture on the next screen. There is. Okay, so let's go over here. We're going to do the 5, 5. 5, 5, and the square root of 10. How would you do that? There are a couple of ways, actually. You know, if you have a calculator, and if your calculator happens to be one of these fancy TI graphing calculators, you may even have something that's written into your calculator to use a theorem called Heron's formula. There's a formula for the area of a triangle if you know the three sides. I will actually tell you, if I was doing a real competition, and if I had Heron's formula programmed into my calculator, I would probably just go and like Heron this thing with like the 5, 5 root 10, 5, 5 root 2, boom, and it's done. Now, of course, that's not really doing proper math, right? That's sort of like saying I've got a really nice, beautiful problem and I whack it with a hammer and then it's done. But yes, you can go Heron this thing. And if anyone's wondering what is this Heron's formula I'm talking about, we're not going to talk about the proof here because that's beyond. But there is a formula that says that if you have any triangle, and if you know the three sides, A, B, and C, this is not a right triangle, just like some random triangle, then what you do is you say let S be the semi-perimeter, A plus B plus C all over 2. And so the area is equal to the square root of S times S minus A times S minus B times S minus C. And so if you actually program this particular function into your calculator, you just go and stuff in 5, 5 root 10 into this thing and out pops the area. Okay, but we're not going to do that. Let's go and do this like the old-fashioned way. The old-fashioned way is to go and say, I've got the 5, 5 root 10. I'm going to turn that triangle a little bit to look like this, and I'm going to cut it in half. So this was my 5, 5 root 10. This is the 5. This is a 5. And now I cut it in half. So this piece right here is root 10 divided by 2. Okay. Well then, I guess it's time to use the good old Pythagorean Theorem. What's this? Well, I can do some squaring and some subtracting. When I look at this, I wonder if I should use some kind of a common factor thing, find a similar triangle. But my numbers are small enough that it won't really matter. So in that case, that's fine. Oh, let me tell you a trick. Yeah, I'm looking at this thing here. It says, what is the area of this dodecagon? I have a little guess. Usually in MATHCOUNTS, it would usually tell you if the answer is a fraction, and it would definitely tell you, I think, if the answer had a square root in it. So you could potentially even just use a calculator and like calculate all these things out, add them up. It might be a nice number. But if I don't do that, let's just go back to here. So good old Pythagorean Theorem. If I want to know what this length is, this will be the square root of 5 squared is 25, minus, I need to square root 10 over 2. That is 10 over 4, because root 10 squared is 10, and 2 squared is 4. So if I put these together, I get a common denominator of, so it's square root of, the whole thing's over 4. 4 times 25 is 100, minus 10 is 90. What an ugly number. Root 90 over 4. Well, I can rewrite that as root 90 and then over 2. Now that I have this, I can find out what is the area of this triangle. The area of a triangle is half base times height. Oftentimes, I like to, if I already have half the base, I like to just take that half base, which is already there, times the height. It's just like, it's already there, that's half base. So the area of this particular thing, the area of this one triangle, is just square root 10 over 2 times square root 90 over 2. Ah, it's going to be good. The reason I say that is because the root 10 times the root 90 is root of 9 times root of 10. So, or you could think of it as root 900, but I think that's less efficient. It's like root 9 times root 10. This is 3 root 10, and there's another root 10. So I actually get 3 times 10, or 30, divided by 2 times 2. And that happens to be 15 divided by 2. So now that's the area of one of these guys. Okay? How about the other guys? For the other guys, I just do the same thing again. I wonder if there's a blank slide on the next one. Let's try. Oh, there is. Okay, so the next one, let's do this. Let's find this. This is 5. This is 5. Let's do this quick now. So if that was the same game, let's play the same game. I have a 5. Cut this in half. I have, on this part, I have a root 2 divided by 2. Sometimes you could even write that as 1 divided by root 2, but we can write it this way for now. Right angle. Okay, let's use our Pythagorean theorem. Square root of 5 squared is 25. Minus root 2 over 2 squared. As I said before, that was like 1 over root 2. That's why the square of it is going to be a half. Okay, let's keep going. So this is equal to square root of 25 minus a half. Whoa, what a weird number. Is that even nice? We're about to find out. 25 minus a half. Huh? I guess so. So that's equal to, if I put it as a fraction, square root of over 2. Ooh, 2 times 25 is 50, minus 1 is 49. That was neat. That's going to divide nicely. This is going to be 7 divided by root 2. I'm actually not going to bother simplifying the denominator. I'm just going to multiply. This is nice. Okay, so if I have that height, half base times height will be root 2 over 2 times 7 over root 2. So let's get the area is equal to half base, root 2 over 2, times height, 7 over root 2. Those cancel, the root 2's cancel, 7 over 2. And at this point, my prediction was right. My prediction was that the answer was going to be a whole number because there was no instruction to express the number in a different way. I have 7 over 2 for each of those skinny things. So each of these skinny things is 7 over 2. And there are 4 of them. Really? Oh, okay. So it looks like there are 4 of these skinny things. And let me read the question again. Is that true? Oh yes, there are 4 of those skinny ones, and there are 8 of the long ones. 8 of the root 10 things. What's the size of a root 10 thing? A root 10 thing has an area of 15 over 2. So now we just put everything together. There are 8 of the 15 over 2, and there are 4 of the 7 over 2. So let's add. So I have 8 of the 15 over 2 plus 4 of the 7 over 2. Here I'm first going to go and cancel away the denominator so I don't have to worry about such big numbers. This goes to 4, this goes to 2, and now what I have to add are 4 times 15, which is 60, plus 2 times 7, which is 14, and that is equal to 74. I'm going to quickly look at the question again, see if that makes sense. Is that what I needed to answer? What is the number of meters squared in the area of the dodecagon? It's good. I think so. Let's see. So I claim the answer is 74. And my assistant says it's good. So we're good. Now that takes us to the last question. What can we do here? And by the way, I should say, I was trying to explain carefully how you'd think through these problems. I guess when you get used to it, these are actually not so bad if you just want to beat them up. Let's see. Ooh, a graph. The bar graphs shown give the probability for Team North and Team South to each score a specified integer number of goals per period. Based on this data, and assuming that the numbers of goals scored by each team are independent of each other, what is the probability that Team South will be in the lead at the end of the first period? Express your answer as a percent to the nearest whole number. I see. So now what we see here is that there's like these different numbers of goals. I have trouble with my vision, so I'm going to look here. I see the 4 and the 5 are at 0%. That's important. And over here, the 4 and the 5 are at 0% also. So now we actually just have a bunch of cases. Like if I look at something like this, what I need to say is, how could it be that Team South would be in the lead? The lead, by the way, means you can't have a tie. So in particular, there's no way for Team South to be in the lead if Team South got 0 goals. I mean, at the best, Team South will have a tie. So you see I'm breaking into cases. I just have to case on Team South having 1 or 2 or 3. And Team South will never have 4 or 5. Let's see what happens. I wonder if there's another chart on the next screen. There is. Let's start adding these up. So I've got the first case. Case number 1 is that the South has 1 goal. Now, in order for the South to have 1 goal and be ahead, how do you do that? Well, South gets 1 goal with a probability of 27%. When you have percents, it's a lot easier to use decimals when there are weird numbers like 27. So that's the chance that South got 1 goal. And to be ahead, I need to know what North got. North has to have gotten 55% over there. So I need to figure out what that is. I usually like to pull out my calculator at the last step. And so let's see what else I need to calculate. There's another case. The next case is that South got 2 goals and ahead. South has 2 and ahead. In order to have 2 goals, my chance is 5%. Remember to put the 0.05. But now, how do you be ahead? How can South be ahead? South can be ahead if North has 0 or 1. So I need to add together these 2%. That one I can do in my head because they're nice. 55% plus 33% is 88%. Okay, I'm going to have to add everything together at the end. And case 3, the third case, is that South has 3 goals and ahead. To get 3 goals is this really, really minuscule 1%. But if South actually got that 1%, it's pretty likely that South is ahead. I need to add these 3 things together. There are 2 ways to do that. One is to add them together, and I had 88 plus 10 is 98. Another way to double check is to say, well, getting these 0, 1, or 2 is exactly the complement. It's 100% minus everything else. And 100% minus 2% is 98%. So I have 0.98. Okay, so in that case, let me read the question again before I pull out my trusty calculator. I need to go and find out that, okay, they're independent. Independent means I could multiply like I was. What's the probability South is in the lead at the end of the first period? I think that's what we had. Express answer as a percent to the nearest whole number. It's calculator time. What happens here? 0.27 times 0.55. This is, by the way, the part that I find scariest, because if you type the numbers wrong into your calculator, the answer is wrong. 0.27 times 0.55 plus 0.05. Make sure you remember to type the 0.05, not the 0.5. 0.05 times 0.88, okay, plus 0.01 times 0.98. And I get an answer of 0.2023 according to my calculator. So when I combine everything here, I get 0.2023, which is approximately 20%. Now, before I go and claim the answer, I'm going to just go and double check my stuff, right? I want to see if it makes sense, right? I just type stuff into a calculator. It's too easy to get the order of operations mixed up or type an extra 0 or not type a 0. So when I look at this, I also want to ballpark it. What should this be? 0.27 times 0.55, that's about 0.3 times 0.5. I kind of made one bigger and the other smaller to compensate. Okay, so like 0.3 times 0.5 is about 0.15. That's about 15% here. What's going on here? That's like 0.05 times 0.9. 0.05 times 0.9, 9 times 5 is 45. But if you move the decimal over 3 times, it's like another about 4.5%. So if I had about 15%, add about 4.5%, that's about 19.5%, about 20%. And how much is this? 1% times something that's practically 1. I think I buy it. I think my answer should be around 20%. So I'm going to go and propose my answer to be 20%. How are we? And it's good! And that finishes the chapter individual competition. So we have managed to go through all of the chapter sprint round and all of the chapter target round. And what you see here is that the way that we went through this was whenever there's extra time, to go and do some double checking. My biggest advice is when you do math counts, make sure that you never sit there waiting for the thing to buzz, for the clock to buzz or whatever. Use your time. And then if you use all your time, you can go and figure out how to do all of these questions a little bit more correctly. And you can see how scared I was of the calculator step. Because everything else I do without the calculator, you may have noticed by now, I always do all the problems where I'm like thinking about this or that and double checking each step. But I can't double check every step of the calculator. So that's unfortunate. But it looks like it worked. Okay, so that finishes the official math counts part. We still have 15 minutes. Here's what I'll do. What I usually have done is during the Ask Math Anythings, I offer to answer any kinds of questions about anything in math. But I think that because we did this we're co-hosting this with Math Counts, it makes sense for me to use this time if people have any questions about Math Counts or middle school math competitions or any of those kinds of things, because that's what we just happened to talk about. Are there any questions? Let's see. I see that some people are saying, ooh, how about the team round? How about the countdown round? You know, those are actually really interesting. You know what? After this, I'll have some more conversations with MathCounts National HQ. And if there's an interest in doing those other problems that we had, or even doing more collaborations like this with MathCounts, I'm actually very open to it. It's just that I want to be respectful of the fact that there's a very exciting week coming up, which is the MathCounts week, and it's already fully scheduled. So I don't want to go and schedule any of these MathCounts discussions, which are directly during that time. Instead, let's start talking about these things. Ooh, I see Winter Rain has asked how to get over the crippling anxiety of the countdown round. All right, if anyone here is wondering what is Winter Rain talking about, the part of MathCounts, which is the spectator sport, is at the very end. After you do all of the different written rounds, then the top 10 people or the top 12 people at Nationals all go up onto stage. And then they have to go and play on a one-on-one, one versus one competition where they're both sitting there and a question pops on the screen. Actually, sort of like what you just saw me doing. It's like, whoa, neat question. Except that they have to go and, they have to do it faster than the other person. And it's actually very, very anxiety-inducing. If you want to get over this, I think the main thing is to think of it as just like, it's just a game. I mean, it's a game, right? It's like, it's not the end of your life. It's not something that is a life or death situation. It's a game. And if you play it like a game, you can sometimes turn that nervous energy into power. So I'll share a little bit about how I approach things. For me, sometimes I am down to the wire. Sometimes there are situations where I really need to get something done and I'm running out of time. And what is useful to do is actually to develop a natural response to stress or pressure, to kind of push away all of the negative parts of the feelings, and instead use that supercharge to wake yourself up. This is actually a normal human response. Normal human response to threats or to stressful situations is fight or flight, right? And what you want to do is you want to use that energy that suddenly surges into you to turn it towards something that's useful. So I'd suggest that. When I was young, I also played a lot of countdown round problems against my brother or against other people in my Math Counts club. That's really fun. I recommend that you do that. Actually, whenever my Math Counts club got together, we really enjoyed doing the countdown round because we weren't really just trying to say who can win. It's actually really fun to do the countdown in person. It's like where you can see the other people, and we had this whole bunch of people in a room, my middle school math club. We were all in the room. There were some buzzers, like legit buzzers that you press on. Buzzers that go beep. Those are fun. And so we really loved doing that, and that helped to reduce the stress. Okay, more questions. What do we have here? Yes, so I'm actually looking at all of these different, I have a number of different monitors which show like questions that are being asked, questions that moderators have chosen. GUYU asks, guessing strats. What are good guessing strategies? As soon as the lag responds, starts again, we'll be back. Good, so the lag is coming back. The lag is recovering. So guessing strategies, what should you do? You may have noticed that a lot of answers are, I guess it's hard to predict the answers, but I might actually guess the number of the problem. For whatever reason, sometimes MathCounts has problem number 15, and the answer is 15. If you really want to guess, you can guess that way. But I'll also say I'm not entirely sure that guessing is really the right way to go. In general, if I was running out of time, I would actually just use the time to go and try to do the next problem. So in some sense, the guessing strat is try to just do the problem if you can. We'll see. Like, do one more question if you can. Okay, what can we do here? What are some more questions that we have? Okay, so we have a question from James Jin, who asks, how long do you recommend to practice MathCounts daily? Is it really that we're only practicing for MathCounts? I would argue that we're just learning math. You see, we were doing this MathCounts stuff today. And maybe if you do MathCounts practice at home, maybe you're doing MathCounts problems. But what you're actually doing is you're learning math. So this is a good thing to do. I mean, I would say that if you have an hour every day where you can do this kind of, let's call it non-textbook math, that's actually not a bad thing. And in middle school, you're lucky enough that you might have that hour. What do I mean? When people go to high school, a lot of people who are in high school will go to school, and then they'll have all kinds of clubs and other activities that they participate in afterwards. And when you go to high school, you generally get quite busy. But if you're in middle school, you haven't yet usually started all these things. So if you actually can set aside an hour to go and play with some interesting and challenging non-traditional problems, that's not bad. If you don't have an hour, spend half an hour. I think that it's healthy to help yourself try to jog that brain and solve problems that you don't know how to answer. Ultimately, what's the goal of all of this? The goal of all of this is to be able to solve problems if you've never seen them before. And MathCounts is full of such things. I see there was another question. Another question that came here was, how long should you read the problem? And how long should you do the problem? So reading is a very important part of this MathCounts. As you saw, there was even a question on this target round earlier where I was like, oh, divide the greater by the lesser, and I interpreted it wrong. You guys saw me do that. And then you saw me kind of going back and rereading it again. It's because my experience is the most common thing to happen is that you kind of know how to do everything, but you just read it wrong. And that just feels awful because you knew how to do the problem. And so I have a personal thing where I'm kind of obsessively always like reprocessing the problem, even while I'm doing it. So I would say you will know for yourself to what level of care you need. And in particular, what you just saw in today's stream is that by being careful, I managed to save myself from getting one problem wrong. Because as I said, I have never done any of these questions before. But had I not done that careful thing, the answer that came at the end would just be wrong answer. So make sure you read it enough, and then you'll get your own sense of how much is needed for that. I saw somebody ask, will you do the state and the national problems? Well, actually, I don't know what the plan is from MathCounts' perspective. I know that there's going to be the state problems that are going to be hosted by Richard Russick next week. And so the state problems are already going to be covered. I don't know what was the plan of the national problems. And if for some reason that this is something that people want to do, I can. And then actually what you'd probably see me doing on the camera is like, good gracious, how do you do this problem? Because you see, this is chapter round. In the chapter MathCounts, I'm like, yeah, I should probably be able to figure these things out. The state ones, I'll have to sweat a bit. And I might be like, yeah, that's an interesting problem. But in the national ones, I would probably start saying, hey, anyone got ideas out there? Who can give me a hand? And, maybe we'll do that. We'll see. I see that somebody has asked, can we have an AMC 8 week? Actually, why not? Good idea. We'll do that next year. So AMC 8 week, I'm very happy to do that next year, but we'll always have to wait until after the exam is safe to talk about. AMC 8, by the way, is not run by MathCounts. AMC 8 is run by the Mathematical Association of America. But these are both great organizations that create fun math problems for you to do. Oh, yes, Shireen Chang said, no, this year, please. You're right. You see, I work at a university. I teach at Carnegie Mellon University. So to us, when we say next year, it's like next school year. So it is this calendar year, but next school year. Great. This is neat. Somebody has asked about snacking tips. Please do not snack on the tips of your pencil. Oh, that's not what you mean. So you mean like tips for like snacks to bring. Well, my understanding is that the competition is so short anyway that it's probably better to just kind of power through the problems and not get distracted with this like apple dripping juice all over your problems. If you're doing the International Math Olympiad, the International Math Olympiad has 4.5 hours, and the people usually bring all kinds of interesting snacks. They bring like bananas, they bring like a loaf of bread, you name it. They bring all kinds of snacks. But on the actual MathCounts, this is such a short time that you probably don't need to have a snack. If you want a snack in between rounds, maybe I would recommend a banana. I'm a big fan of eating bananas because bananas don't drip and you can hold the peel. And when you're done, they're easy to dispose of. And they have a lot of quick energy, except the energy doesn't go straight up to your brain. So my usual way is if I need to have a snack, I'll grab a banana. Wait, bananas are interesting, says Temp ID. I'm not sure what your question means, but I'm a big fan of snacking on bananas. Okay, what else do we have here? So here's a question. what should I do if time is running out and I have several questions left? So you see, you may have noticed that when I'm doing a problem, somehow I would just like do the problem and go all the way through the problem and then go to the next problem. I've discovered that if you kind of half do a problem, you sometimes just don't get all the way through it. I mean, it takes a while to get into the problem to understand whether you can do it or not. And if you spread your time too widely over a lot of problems, you can maybe get like halfway through a lot. But unfortunately, you don't get any points for getting halfway through understanding how to do it. So usually what happens if I see I'm running out of time is that I just let the part of my brain, which is the fight versus flight, is let's ramp into high power mode, but don't freak out doing a little bit of every problem. I usually don't kind of scan forward and see, oh, is there a problem I can do really quickly? And the reason is because the time it takes for me to internalize what is the problem talking about is time that I could have used trying to get another one. And you may have noticed, like even the way I was doing these problems, reading speed is relevant too. This is not just a do math problems competition. It's also a read all of this text efficiently and understand it and read it correctly. If you practice that part, then you can also more efficiently, scan a problem and be like, yes, I can do it. Although I will tell you that I would have one exception. If I was really actually running out of time, here's what I would do. If I saw a problem, and the problem was one of these combinatorial ones, where it's super, super easy to count wrong, I might say, I don't think I want to risk my time on this one, because if I just made one silly mistake because I counted something wrong and you were counting triangles in a weird way, that was a complete waste of time. Whereas somehow algebra type problems, it's quite hard to get those wrong because you just made a silly counting, forgot a case type mistake. So that's what I would say. What other questions can we get here? Okay. This is interesting. So somebody has asked, actually, can I go over old MathCounts packets from previous years in my videos? My thing with MathCounts is this. As I said before, MathCounts is an organization that means a lot to me because for about 3 years of my life, it was the most important thing that I thought was there in the world. That's what I cared about. But I also wanted to respect the copyright of MathCounts because these problems are actually MathCounts' problems. So in all of my daily live streams in the past, I've been extremely careful not to just pick off questions that are official MathCounts problems. Those belong to MathCounts. On the other hand, maybe in the MathCounts National HQ and maybe we'll have a discussion. And if there is something that is useful to help provide this kind of resource to people for long term, we can discuss. But I will say that I myself would never just go and pick up a MathCounts problem and just throw it onto this live stream for you guys, unless it's with their permission and with our collaboration. And actually, I'm saying this because I also hope you do the same whenever you're doing anything with property that's from the internet. This is actually the notion of intellectual property and copyright. So MathCounts has fantastic problems, and they're great to do. But we should also respect the copyrights. What else can we do here? Oh, interesting. Shireen Zhang has asked a question that I don't know the answer to, but maybe this audience does. How many questions does a normal person get right on the sprint and chapter, so I can compare myself against other competitors and study more if needed? Please pick me. Okay, so I think it depends on the city that you live in. You see, I understand that there are some parts of the United States where the top 10 people are getting scores on the chapter, sprint, and target round that are almost perfect. So there are some parts of America which are in that situation. And if that's the case, then unfortunately, it's just a tough place. But you know what? What I'd say is it doesn't mean you're unlucky. Actually, it means you're lucky. You get to be right next to people who are some of the most incredible people in the world. And so you don't need to worry too much about oh, it's not fair. I wish I lived in a place that had less people like this. You know what the people in those other places sometimes say? I wish I could see one of these people who can do all of the problems, and I wonder what they eat for breakfast. You can see they just eat a banana. And that's oh, they're just like me, right? So I'd say it depends on your city. Now, where I live in Pittsburgh, Pennsylvania, we actually, after the competition, all of the coaches in Pittsburgh, Pennsylvania, all get statistics. They all get some charts that say, here were the average scores in this particular city. I don't actually know if this is what happens everywhere in the whole United States. But what I would say is if you're curious what it looks like, the best way is to ask your coach. The Math Counts is actually run by the coach at every school. And the coach should know what were the average scores of people on your school team the last year. And they'll also know how your school team did compared to everywhere else inside your chapter, inside your city. So my answer to this question is, it depends. It really depends. As we saw from the chat, if you live in California, scores are like close to perfect. And if you live in other places, they're not. And so ask your teacher. If you want to know if you're doing well, here's what I'd say. Doesn't matter how many other people are doing. The goal that I always had when I was preparing was to be able to do something like what you just saw me do today, which is called, there is no question that is impossible. Notice I didn't say I could do everything in the time limit. Actually, anyone who was watching yesterday saw that we went over time by half an hour. So you see, the goal is not necessarily just to get a high score on the contest. The goal is to get to a point where if you see any math counts problem, you have the sense that if you just fight with it long enough, you'll be able to come up with something to crack it. And I hope that's a goal we can all walk away from this experience with. With that, I think we've actually hit 5 o'clock p.m. So I will say I really, really enjoyed this opportunity to collaborate with MathCounts National HQ. This, for me, is a great honor to be able to contribute to something that affected my life in an extremely fundamental way. I hope you guys had some fun doing some interesting math problems and watching me struggle to sometimes try to figure out how to do a problem. You see that I also am human in the sense that I will read things wrong, I will find inefficient ways sometimes. That's completely normal. But that's actually the fun of it, because if it was too easy, it would be boring. This also finishes this week's Ask Math Anythings. I will be back, as you know, on Saturday at 8 o'clock. Saturday is tomorrow. I'll be back at 8 o'clock p.m., 8 to 8:45. That's the weekend live show that I do here, where in fact we invite parents even. We discuss kind of things about learning math. We won't really be talking about more than one math problem there. And after that, if you actually liked this live stream stuff that you saw, we'll be doing other problems actually in the Ask Math Anything format as we go onward into the next few days for some time. And the format of those is not actually Math Counts problems. It's where people on the live stream ask all kinds of random questions, and I have to try to answer them. With that, I wish everybody a great weekend, and I'll see some of you tomorrow. And anyone that I don't see, I'm sure I'll run into you at some point again in the future.